give you digital readings, or they give you readings, but this we can see the waveform. So right click before you simulate, right click, add graph, click on add graph. So you find this convenient position, click and drag. So you place your graph there. So that graph will show us exactly what's on the screen. So let's properties. So we want to adjust the maximum voltage. The maximum reading and the minimum reading is between 0 and 12 volts, and our waveform is far exceeds that range. So we can at least we are measuring up to 30 volts, even beyond 30 volts. 42 volts is our V peak. So it means that the upper scale of our y-axis must be more than 42, or at least 42. Let's make it 43. So our minimum should not be 0, because we are going to minus 42, which is negative V peak. So we can make it maybe minus 43 also too, so that our graph will be able to see the full waveform of our AC voltage. So minus 43. Now the time, this is 2 seconds. 2 seconds is probably too short. So we can maybe make it, remember that 0.1 hertz is 10 cycles, 10 complete cycles in 1 second. So with 2 seconds we will always probably see just 20 cycles in 2 seconds. So let's take 50 seconds. Okay, so we see that the scale of our graph has changed, the axes have changed, the time axis and the voltage axis, they've both changed. So let's simulate. Now we can see that the shape, we can see the shape of the actual waveform, so just the way, if this were to be, if we are to run this experiment in a physical laboratory, and we connected our oscilloscope this way, we will actually see this kind of waveform. So it's pretty cool that our virtual oscilloscope can also give us a waveform. So we can see the shape, of the AC voltage as it's rising, reaching the peak and dropping. So it rises up all the way to positive 42, that's the V peak, drops to 0, and then negative V peak, back to 0, up to, you see that it's rising. The bulb, is also corresponding. It's corresponding. Is The brightness is proportional, or is corresponding to the shape of the waveform. So but since this is simulation, there might be some there, it can't be perfectly like the physical implementation. There will be some few glitches here and there. So this is channel 1. You can use 2 channels, but for now, maybe when we get to the module that will, the lecture where we'll talk more exclusively on oscilloscope, then we'll talk about using multiple channels and things like that. So but for now, we're making use of just 1 channel. We've connected it across the load using it as a voltmeter. We are viewing the waveform of the AC voltage, across the load, which is a bulb, a filament lamp, or an incandescent bulb. So that's that about that. If we're able to create a basic electrical circuit or electronic circuit with an AC voltage source, then we connected an ammeter, so we can measure current through. So measure current through the load, which is a filament or a bulb. We can also use a resistor, but we want to see as we want to visualize what is happening as our waveform varies. So let's see if we can adjust the frequency of the AC voltage. So if you left click, um, if you want to change properties, you left click and you right click on whatever instrument you want to alter. And so the filament lamp is on the right. We can connect multiple filament lamps, but probably would do that at other. So if you see, if I run the experiments, of course, like we've done before, we see that we can basically see the fluctuation of the light of intensity. But let's change the frequency to, if it's 1 hertz, let's see how if the fluctuation will be faster. We see that the fluctuation is actually quite faster. It's faster. We can see the oscilloscope graph is that's 50 hertz. Let's go to 50 hertz now. Now it's very fast. But now in physical, the power supply, the AC power supply, AC voltage from PHCN, a public power supply, is also at 50 hertz, but we don't see the fluctuation. But here at 50 hertz we are seeing the fluctuation. So this shows the shortcoming or the limitations of simulation. If this were to be a physical practical, we won't see the blinking. So let's go to 500 hertz. Let's see what happens at 500 hertz. So at 500 hertz, this is what we are supposed to see at even at 50 hertz. So that the bulb is not blinking at all, it's not oscillating at all. So it's basically it's as if it's permanently on, because the flickering or the oscillation is way too fast for our eyes, for the human eyes to catch up with or to follow. So, but at 50 hertz in the simulation, we saw that it was still blinking. That is a limitation of the. You see here that I have my browser home, calculator is on. I have multiple things running. That's antivirus is running. That's a limitation of simulation, or virtual laboratory, because the PC, the processor, is doing so many things at the same time. It is simulating what I'm doing at the same time. It's running antivirus. It's running Microsoft Word. Browser is on. So many things are running simultaneously. So the time, the speed of the simulation is not like real time speed. So at 50 hertz, we're not supposed to see the blinking or the oscillation of the intensity of the bulb. In real life, it will just be as if it's permanently on. But in simulation at 50 hertz, you will still see it. So that's one of the limitations of simulation. But at 500 hertz, definitely we can't see the flickering, we can't see the oscillation of the bulb, even whether it's physical lab experiment or even in simulation. As much as 500 hertz, as high the frequency as high as 500 hertz, you won't see the flickering anymore. So let's get rid of our uh let's go to DC. So we've gotten rid of our oscilloscope. Let's pick a DC. We've talked extensively on AC power source, 80 volts. So let's go to DC voltage source. So you can either go for a battery or a cell. It's basically the same thing. Cell is just a single battery. Batteries are made up of cells, to speak. So we can adjust the voltage of the cell to make it 9 volts, or we can just use a battery that already is already 9 volts. So you can adjust both to. So we can use either of it. So we can make use of a single cell battery or a battery that contains multiple cells. But both of them, so let's use battery, let's delete cell. So adjust the properties, let's make it 30 volts, 30 volt DC. Remember that 30 volts RMS and 30 volt DC are equivalent. They produce the same heating effects, as we said. So this is 30 volts, 30 volts, 30 volt DC. Um, is basically, if it produces the same heating effect as 30 volts RMS. So we've talked about that before. So let's click and drag. Let's complete the circuit as usual. 30 volts DC. And let's see. Let's run the simulation. Now we see here that is the bulb just permanently on. DC does not have frequency. You know, when we changed the properties just now, there was only voltage levels. There was no frequency there. So we see that the current is flowing only one direction. It's not flowing in two directions, only one direction. See that that red bar is not fluctuating. It's not going up and down. It's not changing to blue. It's just permanently on. It's permanently 30 volts, and the current is permanently 2.04 amps. So it's not fluctuating. Current is flowing in one direction. So if we check the current flow output, we see here that current is just flowing in one direction. It's red, permanently red. It's not changing from red to green to blue. And it's current flows from positive terminal down to negative. It flows outward from the positive terminal into negative terminal. So current flows from positive terminal to negative terminal. So let's go back to our measuring instrument. Let's bring out our voltmeter. Let's measure the voltage across the load. Like I said, you measure voltage across a load and current through a load. So click, let's connect across, and then let's run simulation. So we see the voltage is permanently 29.39 volts. So it drops a little bit from 30 volts. So let's use oscilloscope, channel 1 on oscilloscope. Let's connect across the load. We want to view the waveform across the load. Click, drag. Right click, properties, sorry, hard graph. Yeah, click and drag. Right click, check properties. So the maximum voltage, since it's 30 volt now, so let me like 31 volt. Minimum can be 0 actually, because we are not going, this is not AC, this is DC. Let's click. So similarly, can we see that it's just a straight line. It's a straight line at 30 volts, straight line, no oscillation, nothing. Let's alter the properties. Let's make it to maybe around 42. So at 42, we see that it's still a straight line. That straight line there is around 30 volts. So let's stop the simulation. So see, it's just a permanent straight line. It's not no oscillation, no frequency. It's just a straight line. So, and you see correspondingly the filament bulb is not fluctuating, it's not oscillating, it's just permanently on. So that is how DC differs from AC, in that the magnitude just attains one value and remains exactly on that value. So I hope we've been able to, I hope you you properly grasp the concepts of AC and DC voltage and how they are different. We spoke extensively on that on the whiteboard, and now in the virtual laboratory environment we've been able to cement these principles, cement these ideas, and tie it all together by running a couple of mini virtual experiments to show how AC differs from DC, and um, to show this difference by actually looking at the actual waveform of an AC signal and the actual waveform of a DC signal, and to see that AC signal has a frequency and DC signal they have no frequency because it's just a straight line, it's a flat line, you know. And in AC you have RMS voltage and you have peak voltage. So peak voltage is corresponding, it's analogous, or it's kind of like a mirror effect. If cell is a full AC waveform, is you have a positive V peak and a negative V peak. So like in the example, the AC circuit we drew just now, it was about positive 42.43 volts and negative 42.43 volts. So that was the range of peak values for the AC signal that we did just now, and in the DC signal it's just 30 volts, flat out. And we said that the RMS voltage of an AC signal is kind of like the equivalent value in DC that will produce the same heating effect. If we change our load from the filament or the incandescent bulb here, if you change it to a heating element, if you connect a 30-volt DC, the heat, the level of heat, so the temperature of the filament will be the same if you use a 30 RMS volts, um, 30 RMS volts AC. Even though that 30 RMS volts AC voltage is actually rising to 42 volts, is rising to 42 volts and dropping, rising up to 42 volts and dropping to negative 42 volts. The actual fact is that it's actually 30 volts RMS. So we've run a couple of virtual experiments on the in our virtual laboratory. This is live wire. Um, it's a live wire virtual laboratory. There are a lot of virtual laboratories around. There are so many of them. On my PC here, apart from LiveWire, I have another one called Proteus. I don't know if probably before this lecture series ends, maybe one of the other lecture, probably I'll go through Proteus, but I decided to use LiveWire um, for its simplicity. It's a good place to start virtual laboratories. It's a good place to start simulations. So I started with LiveWire for that purpose. Even if you don't go through Proteus, it's basically the same concept, it's the same principle. If you don't make use of Proteus, LiveWire it's basically enough. And apart from Proteus, we also have another one called Multisim. So I personally have not made use of Multisim before. I've not even used Multisim before. But one thing about it is basically they do the same thing. Basically, you have virtual instruments, virtual equipment that you can use in these virtual laboratories, and there are means of you connecting them, and you simulate. You see the output. Just basically what we've done in LiveWire, we can also do it in Proteus. So Proteus has some extra functionality. That's some extra virtual instruments that are not visible, that are not in uh, LiveWire. Proteus has more virtual instruments than LiveWire, but LiveWire yeah, it has the basic ones that are in at this level. So by the time maybe further down the line, 300 level, 400 level, you work extensively more on Proteus. So you might ask, like, is there any need for a virtual laboratory? What's the usefulness of a virtual laboratory? Um, what necessitated its creation in the first place? Since technically it's always better to just do the practical thing, do the actual experiment instead of just simulating. But sometimes, especially like a time like this, there's sometimes where for some reasons you might not be able to run a practical, an actual experiment physically. So virtual experiments, virtual laboratory, they come to the rescue at times like that. And there are times where you even have an actual instrument. You have the instrument with you. You have the cables. You have the supply. You have power supply. You have the connectors. The actual, you are in the laboratory, you have all you need to run the experiment, and for some reason you are getting the kind of output that you're not sure whether that output is actually correct, or maybe you made a mistake. So sometimes you can verify results of physical experiments by going to the virtual laboratory and running that same experiment. So then you compare the results. So before virtual laboratories, when they are being created, when these virtual instruments are being modeled, they are modeled to mimic an ideal um, non-faulty physical laboratory equipment or laboratory instrument. So sometimes if your physical um, laboratory equipment or laboratory instrument is faulty, if it has a fault, and you suspect that it has a fault, you can just check the virtual one, the virtual instrument, the virtual laboratory equipment. Just check it out. And you run the simulation and you see the output, and you can use that to you can compare the result and then determine whether or not your physical laboratory instrument or laboratory equipment is faulty or not. So I hope you've enjoyed this brief introduction to virtual laboratory environments, and you've been able to grasp the basic ideas behind AC and DC voltage sources, and and hopefully by the time we resume fully, or we get back to the laboratory, and we get our hands on on the physical uh, laboratory equipment, it won't be strange to you. So thank you for staying tuned with me today's lecture. Um, See you soon for the module 2 of this video lecture series. Thank you.